Last class, I gave you one theorem. Suppose continuous mappings. We know that when a function is continuous, a function f is continuous on x, if and only if f inverse g is open in x, whenever g is an open set in y. This is one important theorem. This you learn. Okay. Then, see, let us define just while teaching offline, I did not touch this topic, that is functional algebras. Functional algebras. Because these are very easy, I thought of teaching offline also. The set of all continuous functions on x is denoted by CXR and CXC. Okay, so first one is suppose you have V is a vector space. We know that how do you define a vector space? All of you remember? F is a field. V is any non-empty set. V is any non-empty set. Then we say that V is a vector space over the field F. V is a vector space over the field F if for every, that means there exists a binary operation called vector addition, such with respect to which V is an abelian group. V plus is an abelian group and it satisfies scalar multiplication. That is, whenever A belongs to F, alpha belongs to V, A alpha belongs to V. And also you have, and it satisfies properties like A into alpha plus beta is equal to A alpha plus A beta and A plus B into alpha is equal to A alpha plus B alpha and 1 into alpha is equal to alpha and alpha AB into alpha is equal to A into B alpha. We have seen many examples of these vector spaces also. Now, see here, suppose if multiplication satisfies the properties of associativity and the distributive laws are satisfied, then we say that the linear space, vector space VF is called algebra. If it satisfies commutative property also, it is a commutative algebra. Okay. And we define, see, suppose X is a topological space. Suppose X is a topological space. We take, where is the pen? Okay, text lost. 1 minute, Amma, 1 minute. This pen has gone somewhere. So we define CXR is set of all functions F such that F from X to R is a continuous and bounded function. So we know that whenever F and G are continuous, we know that F plus G is continuous and alpha is any constant, alpha is continuous. Okay. So this kind of problems you will get for 6 marks. Students, is the screen is visible? Hello?
No, ma'am.
No, ma'am.
No. 1 minute. Now?
Yes, ma'am.
Ma'am.
Okay. See, we define CXR. CXR is the set of all F such that F from X to R is a bounded, continuous, real function. Okay. How you define join and meet? See, we define F join C, F join G at X is equal to maximum of F of X comma G of X. And F meet G at X as minimum of F of X and G of X. Just these are only the notations which we are going to use. So here first lemma we will see. For F comma G belongs to CXR. That means the set of all continuous functions on real field. CXC means the set of all continuous functions on complex field. So you have F comma G belongs to CXR. We have F plus G comma alpha F belongs to alpha F belongs to CXR. Just entire unit, our aim is to prove that this will form a linear space, and also sometimes see here we prove that sum of two continuous functions is continuous, product of two continuous functions is continuous, and we prove that this CXR is a Banach space. CXR is a Banach space. Banach space means every Cauchy sequence is convergent. That we will prove. So now see here how to prove this lemma. That means whenever F and G are continuous functions, we have to prove that F plus G is also continuous and bounded function, and alpha F is also continuous and bounded function. Now here, suppose F comma G belongs to CXR. What do you mean by this? You know that F comma G are bounded and continuous. These are bounded and continuous functions. Now what we have to prove? We have to, what do you mean by boundedness? Immediately you should know. Say that if F is bounded, then there exists a real number M1 greater than 0 and M2 greater than 0 such that mod F of X is less than M1 and mod F of G of X is less than M2. So then what you will get? You will get mod F of X or F plus G at X is equal to mod F of X plus G of X, which is less than or equal to mod F of X plus mod G of X, so which is less than M1 plus M2. That means whenever F and G are bounded, F plus G is also bounded. Okay. Now we prove that f plus g is also continuous. Tell me what is the definition of continuous function. Suppose f comma g are continuous at x naught. Then what you will get for given epsilon greater than 0. Okay. There exists a neighborhood g1 of x naught such that mod f of x minus g of x naught, sorry, mod f of x minus f of x naught is less than epsilon by 2, and mod g of x minus g of x naught is less than epsilon by 2. Students, if you are feeling tough with the theory, this is like a problem type only, no? This kind of theorem, try to learn. F and G are continuous at x naught means for every epsilon greater than 0, there exists a neighborhood G1 such that mod f of x minus f of x naught is less than epsilon by 2. Mod g of x minus g of x naught is less than epsilon by 2. Now, what is our aim? We have to prove that f plus g is continuous. To prove f plus g is continuous, what we will do? Mod f of f plus g at x minus f plus g at x naught. Okay, this is nothing but mod f of x plus g of x plus minus f of x naught minus g of x naught, which is nothing but mod f of x minus f of x naught plus mod g of x minus g of x naught, which is less than epsilon by 2 plus epsilon by 2 equal to epsilon. That means whenever f and g are continuous at x naught, you have f plus g is also continuous at x naught. So what do you mean? Whenever f and g belongs to CXR, that is the set of bounded and continuous functions on x, then whenever f and g are continuous and bounded functions on x, then you have f plus g is also bounded and f plus g is also continuous. Students, am I clear? Hello?
Yes, ma'am.
This will
Clear, ma'am.
Yeah, this will be easy. Just sometimes because very easy. That is the reason I did not teach you offline. So now try to follow this. Again, what you have to prove? Alpha f, coming to alpha f. So whenever f is bounded, you have mod f of x is less than some m1. Tell me what is mod alpha of f of x? This is mod alpha into mod f of x. This is less than m1, alpha into m1 or m1 into mod alpha. So that is the reason always you have, whenever f of x is bounded, alpha into f of x is also bounded. If alpha equal to 0, nothing to prove. Okay. And if alpha not equal to 0, here you take alpha not equal to 0. So now we prove that whenever f is continuous, alpha f is also continuous. For this, consider alpha f at x minus alpha f at x naught. This is mod alpha into mod f of x minus f of x naught. Because f is continuous, this is less than epsilon. So this is mod alpha into epsilon by 2. Mod alpha into epsilon by 2, or you get mod f of x minus, nothing, you take epsilon only, mod f of x minus f of x naught is less than mod alpha into, sorry, 1 minute. Here what we have to prove? You have to prove that alpha f at x, alpha f is continuous. To prove alpha f is continuous, consider mod alpha f x minus alpha f at x naught, which is mod alpha into mod f of x minus f of x naught. That means if f is continuous means mod alpha into mod f of x minus f of x naught is less than alpha. So this is, you have mod alpha into epsilon. So if you choose epsilon is like epsilon by mod alpha, for alpha mod alpha not equal to 0, we have mod alpha f at x minus alpha f at x naught is less than epsilon. Therefore, you get alpha f is continuous. Therefore, you have alpha f is bounded and alpha f is continuous means alpha f belongs to CXR. So, what do you mean by this? CXR is closed with respect to addition and scalar multiplication. Scalar multiplication. And similarly, you can prove whenever f and g are continuous, fg is also continuous. Okay, Andy? Fg is continuous. Now again, fg is continuous and f by g is also continuous. So one more theorem is there, which we will do in the next week. Just this is revision of the old items, old lessons. Now today, last class, we are defining T1 spaces and T2 spaces. In the last class, what I explained about T1 space, so separation axons. What do you mean by a separation? A topological space X is said to be a T1 space. A topological space X is said to be a T1 space. If any two distinct points, X and Y in X, there exists open sets G and H such that X belongs to G minus H and Y belongs to H minus G. Okay, Andy? So last class I explained this T1 space. Separation means two sets are separated by 2 points. See here. This is your topological space X. Okay. This is your set G. This is your set H. You have X here and here Y here. So a topological space X is a T1 space. X is a T1 space if there exists open sets G and H such that X belongs to G minus H and Y belongs to H minus G. So this is this one. Now, what do you mean by a T2 space? T2 space is also known as Hausdorff space. Hausdorff space means it is a T2 space for any X not equal to Y. There exists two distinct open sets G and H. This is G, this is H. Here you have X belongs to G and here Y belongs to H, where G intersection H is non-empty. So this is T2 space and the above one is T1 space. Okay. From this, I explained one theorem. Let X be a Hausdorff space. Every Hausdorff space is a T1 space, but the T1 space need not be a Hausdorff space. Now today, let us let us discuss about regular spaces and normal spaces. Students, all the definitions are very important for 6 marks. They will ask you to define T2 space or regular space or normal spaces. Okay. Now here in T1 space, we have seen how 2 points are separated by 2 distinct open sets. In T2 space, 2 distinct points are separated by 2 disjoint sets. 2 disjoint sets. Now, let us discuss about a completely regular space. Or first, completely means first let us discuss about a regular space. See, what do you mean by a regular space? A T1 space is called a regular space. A T1 space is called a regular space if for X belongs to X and any closed set A, for any closed set A not containing X, not containing X, there exists open sets G comma H such that you have X belongs to G and closed set A is a subset of H, and as usual G intersection H is non-empty, that is they are disjoint. Okay, so if you know the concepts of T1 space, Hausdorff space, regular space and normal space, then only you will be able to understand this Urysohn's embedding theorem, Urysohn's lemma, T's extension theorem. These three theorems are very important theorems of topology. So here, just let us focus on the concepts. Students, any more doubts in defining a T1 space? T1 space means 2 points are separated by 2 open sets. X not equal to Y means there is open set G such that X belongs to G but not to H. Y means Y belongs to H but not to G. That is the concept. 2 points are separated by 2 open sets. There G and H can have common points also. But for Hausdorff space, 2 sets cannot have common points. 2 points are separated by 2 disjoint sets. That means you take 2 sections in the same class. 2 sections. That means, see, suppose in a school for 10th class, there are 2 sections A and B. They belong to the same class, but student of class A does not belong to student of class B. So that is the example of T1 space. Okay. So T2 space means where students will combine for some social class, they will be combined. Suppose there are some common points, such common chapters for 10th A and 10th B means what we will do, we will combine the sections. So that is the T1 space. T2 space means G and H both are disjoint. Okay. 1 minute. Hello. Cheppa.
Video call है? Saya gue pergi ya.
Now you have a regular space. What is a regular space? A T1 space is called a regular space if for every x belongs to x and a closed set. That means, see, in T1 space, 2 points are separated by 2 sets. In T2 space, 2 points are separated by 2 disjoint sets. In regular space, 1 point and closed set are separated by 2 disjoint sets. So here how it will be, see, there is, this is your x, this is point x, x belongs to G. This is your x belongs to G. And A is a subset of H. This is A, this is H. But A does not contain H. So these two are separated. So a T1 space is called a regular space if for every x belongs to x and any closed set A not containing x, there exists G belongs to H such that x belongs to G and A is a subset of H. A is closed set and A is a subset of H such that G intersection H is empty. So this is known as a regular space. So you have to prove that, see, clearly whenever G and H have no common points, you can think of a Hausdorff space. So what do you mean? Every regular space is a Hausdorff space. Immediate. Tell me. Any doubt?
No doubt है पूछो.
Okay. Now, see, immediate consequence after defining the regular space, you have to immediate consequences. Every regular space, every regular space is a Hausdorff space. Every regular space is a Hausdorff space. So how you prove that? Suppose X is a regular space. You have X is a regular space. So what do you mean? First of all, because see, what regular space means, immediately what does it follow, Nana? X is a T1 space. Because a T1 space is called a regular space. So X is a T1 space. Whenever X is a T1 space, you have, we know that in a T1 space, singleton sets are closed. For every X belongs to X. Now, if you take X not equal to Y, then Y is closed and not containing X. Y is closed and not containing. So what do you mean? There exists open sets G and H such that you have X belongs to G, singleton Y is a subset of H and G intersection H is empty. Therefore, every regular space is a T2 space. Every regular space is a T2 space. Converse is not true, but now let us move on to a complete regular space. Students, am I clear with this? Are you clear with regular space, T1 space, T2 space? Hello?
Yes, ma'am.
So this you learn, for short answers, you learn this. And the next one, completely regular spaces. Completely regular spaces. Completely regular space means it is related to a function. A T1 space X is said to be completely regular if for every X belongs to X and closed set a T1 space X is said to be regular a T1 space X is said to be completely regular, completely regular if for any X belongs to X, for any closed set A in X not containing X, there exists a continuous map. There exists a continuous map F from X to 0, 1 such that F of X is 1 and F of A is 0 for all A belongs to A. Once again, listen carefully. A T1 space X is said to be completely regular. Regular space means a T1 space is said to be regular if a point and closed set are separated by two disjoint sets.
Distant set.
Yeah. Here, completely regular means whenever you have such a separation, that means for any X belongs to X and closed set A in X not containing X, there exists two disjoint open sets, and here there exists a mapping, continuous mapping, such that F of X equal to 1, F of A equal to 0. What do you mean by that? Here, point and set are separated by means of a continuous function. There, points are separated by two disjoint sets. Here, points are separated by continuous function. A T1 space X is said to be completely regular. Read the definition only for more than 2 to 3 times until you digest the concept. Then only you can prove the big theorems. Just these 3 theorems I am going to explain. One is T's extension theorem, Urysohn's embedding theorem, and Urysohn's lemma. These 3. A T1 space X is said to be completely regular if for any X belongs to X and a closed set A not containing X, there exists a continuous mapping F from X to 0, 1 such that F of X equal to 1 and F of A equal to 0 for all A belongs to A. That means immediate consequence is next theorem. This kind of results you can learn for 6 marks. Every completely regular space, every completely regular space is regular. Every completely regular space is regular. Okay. So first proof. Suppose X is completely regular. Means X is a T1 space. Every completely regular space is a T1 space. Now see, you take one element, X belongs to X and A is closed set in X not containing X. Not containing X. So because F is completely regular, our assumption on X is completely regular. So there exists a mapping F from capital X to 0, 1 such that you take F of X is equal to 1 because A is not containing X kada. You have F of X is 1 and F of A equal to 0 for all A belongs to A. Okay. So then what you will do, you split 0, 1 like this. You split the closed interval 0, 1 into 2 sets like 0, 1 by 2, 1. So whenever f is continuous, you have f inverse 0, 1 by 2 and f inverse 1 by 2, 1 or disjoint open sets. They are disjoint open sets in X. Why, Nana? Because you have 0, 1 by 2, 1 by 2, 1 unnai kada. These are open in 0, 1. We know that every open interval is an open set. So 0, 1 by 2 is open, 1 by 2, 1 is open in X. So what do you mean by this? You have X is a regular space. Therefore, X is a regular space. So every completely regular space is regular. Why I have taken 1 by 2 ma? Generally we go by what you call bisection method. So we make into 2 because see, I told you many times, if you want to prove, you focus on 2 things. What is given, what we have to prove. Already given that X is a completely regular space, you have to prove that X is regular. To prove X is regular, what you have to prove? You have to take a closed set A of X and a point X which is not in A such that G intersection H is empty. For this, there exists 2 open sets G and H such that G intersection H is empty. So therefore, already you have X is a T1 space and you take X belongs to X and a closed set which do not contain X. So because X is a completely regular space, there exists a mapping or continuous mapping f from X to 0, 1 such that f of X is 1 and f of A equal to 0 for every A belongs to capital A. So you divide 0, 1 into 2 sets. Okay. So you take f inverse. We know now one theorem is there. F is continuous. Sorry, if you take like this, f from X to Y is continuous whenever f inverse G is open in X for G open in Y. For any open set G in Y, you have f inverse G is open. So you have whenever f is continuous, means you have f inverse 0, 1 by 2, f inverse 1 by 2, 1 or 2 disjoint open sets in X. Therefore, you are able to find 2 disjoint open sets such that f of X is 1 and f of A is 0. You are able to find 2 open sets such that G intersection H is empty. Therefore, X is a regular space. Every completely regular space is a regular space. Similarly, every regular space is a Hausdorff space. We proved, no? Therefore, every completely regular space, see, you know that every regular space is Hausdorff. Every regular space is Hausdorff. So on the whole, what you have, every regular space is Hausdorff and completely regular space is regular. So what do you mean by that? Every completely regular space is a Hausdorff space. Now, one more important is normal spaces. Normal spaces. So how you define a normal space? A normal space is a T1 space. A T1 space, X is said to be normal if any two, open sets kadanడి, only closed sets. If any two disjoint closed sets, any two disjoint closed sets, capital A and B in X, there exists open sets G and X, G and H in X, such that A is a subset of G, B is a subset of H, and G intersection H is empty. So a T1 space X is said to be normal. See, just how he is developing the theory, you observe carefully. T1 space means 2 points are separated by 2 sets. T2 space means 2 points are separated by 2 disjoint sets. Okay, regular space means what he is saying? Regular space means 1 point and 1 closed set. 1 point and 1 closed set. That closed set should not have this point. 1 point and 1 closed set are separated by 2 disjoint open sets. And what do you mean by completely regular space? 1 point and 1 closed set are separated by continuous mapping. But normal space is a little bit go forward. When we are able to separate points, why can't we separate sets also? So you take 2 sets A and B. 2 sets A and B are separated by 2 open sets G and H, such that A is a subset of G and B is a subset of H, and G intersection H is empty. Okay. In other words, a T1 space is a normal space if any two disjoint closed sets are separated by open sets. Just to read the definition. Students, is this clear? Hello?
Yes, ma'am. Clear, ma'am.
Clear, ma'am.
Are you able to follow my voice, or any disturbances are coming? Okay, no?
The voice okay, ma'am.
A T1 space X is said to be a normal space if any two disjoint closed sets A and B in X, there exists open sets G and H such that A is subset of G, B is subset of H. Okay, like this. Like this. A is a subset of G, B is a subset of H, but G and H have no common points. Okay.
Okay, ma'am.
Next. So from this, we can prove every metric space is normal and every compact Hausdorff space is normal. So anyhow, last 7 minutes is there. You have any doubts means you ask ma. Because if I start theorem also, I may not be able to complete. So let us do Urison's lemma in the afternoon. Okay.
Yes, ma'am.
If any class you are free, you make a call to me. I will try to take that. We have to do 3 theorems. With that, syllabus will be over. Urison's lemma, T's extension theorem, and Urison's embedding theorem. 3 theorems I will teach. Okay. And then connection, you have to do connected spaces. Any doubts you can ask me. Any questions? Just to go through definitions.
मैम आपके वॉइस नहीं आ रहा।
मैम वॉइस स्टार्ट लग मैम.
See, every compact Hausdorff space is normal. So what do you mean by compact space? Every open cover has a finite subcover. Suppose X be a compact Hausdorff space, then T1, it is a T1 space. So in order to prove X is a normal space, what you have to prove? You have to prove that two disjoint sets A and B, we prove there exists G and H such that G intersection H is empty. For that for that take two sets, let A and B be two disjoint sets, closed sets in X. We know that any closed subspace is a compact set, which implies A comma B are compact in X. We proved now every closed subspace Y is a compact. Therefore, A and B are compact. So what you mean by this? You have compact means you have P1 space. You have A belongs to some G alpha. See, what is this? It is T1 space, compact Hausdorff space. Hausdorff space means a point and closed set are separated by two disjoint sets. So what do you mean? So for any A belongs to A, there exists two open sets, G alpha and H alpha, such that A belongs to G alpha, B is a subset of H alpha, and G alpha intersection H alpha is empty. Okay. Now you take G alpha, open set noma, for alpha belongs to delta. This is open cover. Open cover for A. So A is compact means there exists A1, A2, etc. AN. Every open cover will have a finite subcover. That is, A is having finite subcover, intersection J is equal to 1 to N, G A I, that is G alpha I. So you can take G equal to intersection of G AI, H is the intersection of H AI. So that you will get G intersection H is empty. So you are done. You have A belongs to G alpha, B belongs to H, and G intersection H is empty. Therefore, X is normal. So every compact Hausdorff space is normal. How you prove? You have to take two closed sets A and B. You have to prove A and B are separated by two disjoint sets. You have to find G and H such that G intersection H is empty. Because A is a closed subset of compact set, it is also compact. A is a compact set, B is also compact set. In a compact set, every open cover will have a finite subcover. So whenever G alpha and H alpha are disjoint, their intersection G and H are also disjoint. Therefore, X is normal. Okay, ma? So with this, I am stopping my lesson. So next class, we will do Urison's lemma. Okay?
Okay, ma'am.
Okay.
Okay, ma'am.
Yeah.
Thank
For this, for the next class, come prepared with the concepts, Nana. Have clear idea about T1 space, T2 space, normal space, regular space. Okay?
Okay, ma'am.
Okay, ma'am.
Yeah.
Okay. Thank you, ma'am.
Thank
Come.
హలో హలో దివ్య హలో
హలో
మీరు అంబేద్కర్ యూనివర్సిటీ హలో హలో
హలో
గ్రూప్ క్రియేట్ చేశారా మొన్న సార్?